Before we talk about nucleophilic acyl substitution reactions, which are great for the interconversion of carboxylic acid derivatives, we're first going to talk about other preparation methods. You'll see when we think about reactivity, I like to think about acid halides, followed by anhydrides, followed by esters, followed by amides, followed by nitriles. We're not going to discuss any other ways to make anhydrides, and I save esters for last because it ties in nicely to other types of nucleophilic acyl substitution reactions. For the preparation of acyl halides, we can start with carboxylic acids. These can be treated with thionyl chloride to give the acid chloride. Alternatively, we can use oxalyl chloride, which would give the same acid chloride. If we need the acid bromide, we could instead use phosphorus tribromide, and that will convert a carboxylic acid to an acid bromide. You're not responsible for the mechanisms of how these reactions work, but you can look in your textbook if you're curious. Amides can be prepared from carboxylic acids or from nitriles. The preparation of amides, starting from carboxylic acids, involves reaction with an amine. This starts out as an acid-base reaction, giving us an ammonium carboxylate salt as an intermediate, but then if this is heated up, it leads to the loss of water, forming an amide bond. For example, here we have benzoic acid, and this can be reacted with ethylamine to form this carboxylate salt, followed by loss of water to give N-ethyl benzamide. This method is useful for the industrial preparation of particular amides and for some lab scale syntheses, but this is not very generally useful on the lab scale, mostly because of the excessive temperature. But a number of coupling reagents have been developed, such as DCC, which is dicyclohexyl carbodiimide, and this compound has been very important in terms of peptide synthesis, in particular for solid phase peptide synthesis. Another way to make amides is by starting with a nitrile and carrying out a hydrolysis. A nitrile can be hydrolyzed to a carboxylic acid, but this proceeds through an amide. So if you use mild enough conditions, you can get this reaction to happen, whereas if you use stronger conditions, you will get this reaction to occur. Hydrolysis of a nitrile can occur either under acidic or basic conditions. Under basic conditions, the hydroxide is the nucleophile that adds to the nitrile carbon, pushing these electrons onto the nitrogen. Giving this intermediate. The nitrogen can grab off a proton from water, giving this, which is an enol tautomer of an amide. This can tautomerize, where hydroxide, for example, could grab off this proton, put those electrons here to form a C double bond O, push these electrons onto the nitrogen, and then this can grab a proton from water, forming the amide. Several of these intermediates that are drawn here are stabilized by resonance. And so you can gain additional practice in understanding mechanisms by working through the resonance structures as well. If instead the hydrolysis is carried out under acidic conditions, then this would start with the nitrile getting protonated, giving this intermediate. Next, water can act as a nucleophile, share its electrons with this carbon, pushing these electrons onto the nitrogen. And then water can act as a base, grab off this proton, giving us the enol tautomer of an amide, just like we had here. Because this is under acidic conditions, not basic conditions, the tautomerization won't look exactly the same. You can work through the tautomerization under acidic conditions to show how this enol is converted to an amide. Nitriles can be prepared by nucleophilic substitution as well as nucleophilic addition. Here we have a primary alkyl halide, and if this is treated with cyanide, this will act as the nucleophile, pushing away bromine as a leaving group, giving us our substitution product. With a secondary alkyl halide or alkyl tosylate, something with a good leaving group, the nitrile can again act as a nucleophile, leading to primarily the substitution product. However, if we have a tertiary alkyl halide or alkyl tosylate and we try to do substitution, instead, this is going to give us E2 elimination. And very, very little of the substitution product. So because cyanide is a mild enough base, you will get SN2 substitution using methyl primary or secondary alkyl halides, but you still can't get SN2 substitution with a tertiary. An aldehyde or ketone can be treated with cyanide. This will act as a nucleophile, pushing these electrons up onto the oxygen, giving as an intermediate this. And then under mild acid conditions, the O- can grab off the H+ to give a cyanohydrin product. Nitriles can also be prepared from amides by dehydration. An amide, for example, can be treated with P2O5 phosphorus pentoxide or POCl3 phosphorus oxychloride, and this will carry out a dehydration with the loss of water, leading to the formation of a nitrile. As another example, benzamide can be treated with phosphorus pentoxide or phosphorus oxychloride, resulting in the formation of benzonitrile plus water. Notice what we have here is an aryl nitrile. There is a specific method to make aryl nitriles from aryl diazonium salts, which we cover in another chapter.